this video, we will learn about the basics of feature engineering, and we will learn about one particular technique of feature engineering called one-hot encoding. One of the common way to format the data is by working with categorical variables or features. Categorical variables have discrete values and they represent a category of class. Some machine learning algorithms support categorical variables while others don't. And that is why feature engineering technique called categorical encoding is applied to the data, which converts categorical data to a numerical form. In one-hot encoding, the values in a feature are spread to multiple flag features, and these flag values can be assigned as 0 or 1. The binarization of data represents the relationship between encoded as well as the non-encoded features. Therefore, in this technique, value of 1 is assigned to a category flag that indicates the feature is existent in a particular observation. If a value of 0 is assigned, that would mean the feature is not existent in a particular observation. In this video, we will learn about another feature engineering technique called binning, which is a process of transforming numerical values into categorical counterparts. In binning, different values are grouped into bins, thereby converting numerical features to categorical ones. Binning can also be used to transform categorical values to other categories. Data binning is also called as bucketing, and it minimizes the effects of small observations error in the data. It typically has a smoothing effect on the input data and often prevents overfitting models, especially in situations where the data sets are limited or small. Binning can be performed in two simple ways, namely equal frequency binning or equal width binning. In equal frequency binning, the bins have the same frequency, while in equal width binning, the range of each bin is equal and is defined by a simple formula. In this video, we will learn about another of the feature engineering technique called transformations. Many machine learning models work on the assumption that data follows a normal distribution, which is often not the case in real-world datasets. The real-world datasets often have a skewed distribution. Therefore, data transformations need to be applied to these features to convert the skewed distributions to a normal distribution, thereby increasing model performance accuracies. The simplest and most commonly used data transformation is log transformation, which changes the values to a natural log or a log base 10, making the data less skewed, especially for datasets which are skewed to the right. Also, the log transformation significantly transforms the distribution shape. Another commonly used transformation is square root transformation. In this transformation, the shape of distribution is changed. This transformation is less effective than log transformation and can only be applied to positive numbers. An advantage of using square root transformation is that it can be applied to zero values as well. Another commonly used transformation is reciprocal transformation. This transformation is performed when a powerful radical transformation is needed. In reciprocal transformation, the larger values become smaller and vice versa. It, however, preserves the order amongst the values of the same sign. In this video, we will learn about another of feature engineering technique called data scaling. We will also discuss normalization technique and understand why it is important to standardize independent variables. Scaling is a feature engineering technique that is used to optimize data for machine learning models, and it helps them make better predictions. Often in the real world, features have value ranges that are different from each other. For example, a feature can have a range of value from 0 to 20, while another feature might have values ranging from 0 to 100. In such cases, it is likely that the machine learning algorithm assume that features that have higher range is more important than the feature having the lower range. To avoid such situations, scaling is performed to ensure numerical features have the same range. The standardization of range in numerical data is often a prerequisite for many machine learning models. Now, let us have a look at two of the most commonly used scaling techniques. The most commonly used technique is called normalization, where data is scaled in the 0 to 1 range. While performing normalization, the inherent distribution in the data is preserved. Another type of scaling that is often used is called standard scaling. Here, the mean is removed from each observation of the feature, and the resultant is then divided by the standard deviation of the feature. In this video, we will learn about another of feature engineering technique called data shuffling. Data shuffling is a technique that is used to mix up data randomly within an attribute or a set of attributes. In data shuffling, however, users can optionally retain the logical relationship between different attributes as well. Shuffling the data helps remove any sequential biases that can creep into a data set and can also help in building more robust training models in machine learning. The data can be shuffled randomly if the inherent characteristic of the data need to be preserved for each feature. If, however, a certain relationship between different columns needs to be preserved, they can be combined to create designated groups, and then shuffling can happen together for the attributes within the defined group. Additionally, we can also create partitions that help preserve any dependencies between attributes, whereby the data is shuffled only within the partitions and the value for different partitions are never associated. Simply put, this shuffles the data in rows that share the same values for designated feature. Hi, in this video we will review some code that performs some of the feature engineering techniques on a sample data set. In the code, we will be covering binning and encoding techniques on the sample data. On our screen, we are running a Jupyter notebook with Python 3.8. The first step would be to import the required packages and the sample data set. In the code cell just below import packages and dataset header, we have done just that. In code line 2 of the cell, we have imported the pandas package with the syntax import pandas as PD. Then in code line number 5, we've imported the dataset on which we would be running our feature engineering techniques. We have done the import of the dataset using the syntax pd.read_csv with the file name in the brackets. We have saved this pandas data frame in an object called data. In line number 6, we are just displaying the top 6 rows of this dataset. So let us now run the first code cell of the Python Jupyter notebook. On running the cell, the output is now displayed in output cell 1. In the table observed in the output, we notice that the dataset contains 4 columns, that is ID, petal length cm, petal width cm, and species. The species column represents the different categories of flowers represented in the dataset, and petal length and petal width column represent the features of the species represented in the dataset. The ID column represents the sequential numbering of the rows in the dataset, and therefore can be ignored. Now, let us first review how the categorical encoding can be implemented on a sample dataset. For that, let us expand the code under categorical heading header. Our dataset includes 3 kinds of species of flowers represented 3 classes or categories. So, in order to make the categories ML algorithm friendly, we should consider converting these categories from text into numerical categories. We could do that by giving each category a numerical code. And we have done just that in the code cell under categorical encoding. First of all, in line 2 of the cell, we have set the data type of species column as type category by using the syntax data with species in square brackets is made equal to data with species in square bracket followed by dot as type with category keyword in round brackets. Then in line number 3, we have created a new column in the dataset and called it species underscore category. We have done this using the syntax data with species underscore category in square brackets is made equal to data with species in square bracket followed by dot cat followed by dot codes. Then in the subsequent line, that is line number 4, we are simply displaying the dataset. On running the code cell, we can observe the resultant table in output cell number 2. On observing the data table, we notice that a species underscore category column is appended to the dataset. If we observe the rows of our data table, we observe that values under the species column are given some corresponding numerical value in the species underscore category column. For example, in row number 149, species Iris-virginica is given a species category of number 2, whereas in row number 0 or in row number 1, species category Iris-centosa is given a species category of number 0. Now, if we were to use a machine learning algorithm on this dataset, we would be removing the column species and would be using the species underscore category column, as that would be an easier feature for our ML algorithm to understand. Now, let us review the code and perform binning type of feature engineering technique to our dataset. In the first code cell under the binning header, we observe that we have given a code with syntax data.describe. On running the cell, we would be able to review the summary statistics of the dataset. On scrolling down, we can observe the output in output cell number 3. At this step, we need to first identify the need to perform binning on our dataset. In the table in the output cell 3, if we observe the rows in the values in the index column, we observe values such as mean, min, max, and etc. Therefore, the rows of the index column describe the statistics summary of the dataset. And correspondingly, if we look at the values under petal length CM column, we observe a continuous range of numerical values with minimum value as 1 and maximum value of 6.9. Using the continuous values under the petal length CM as it is would lead to overfitting in our ML algorithm. So we may be better off if we could provide some kind of a labeling to the values under petal length CM column. We could define the values under this column with low, mid, or high labels. In the data at hand, we could say that the first 25th percentile values can be characterized as the low petal length, and the values between 25th and 75th percentile can be categorized as mid petal length, and values greater than 75th percentile can be characterized as high petal length. As observed in the summary table, the 25th percentile, the 75th percentile, and the max values are represented by 1.6, 5.1, and 6.9 respectively. We will be using these values in the next step. In the next code cell, line number 1, we have created a new column with the syntax data followed by petal length underscore class in square brackets. This new column is made equal to pd.cut with respective parameters for cut method in parentheses. The first parameter is the values of the petal length CM column in the dataset. The second parameter of the cut function is bins, which is made equal to 0, 1.6, 5.1, and 6.9 in square brackets. Consequently, the third parameter of the cut function is labels, which is made equal to low, mid, high, given under as a list in square brackets. Here, the low value is used for values that are less than 1.6, mid value is used for values between 1.6 and 5.1, and high is used for values greater than 5.1. Now we are ready to run the cell. On scrolling down, we can observe the resultant table in output cell 4. Now, if you observe the values in the last column that's newly added with the name petal length underscore class, we observe that the values range between low, mid, and high. For example, in row 4, we observe that petal length underscore class value is termed as low, where the petal length CM value is 1.4. Similarly, in row 145 and 146, we observe that the petal length underscore values are high and mid for petal length CM values that are 5.2 and 5 respectively. Now, as a consequence of this table, we may be better off to remove petal length CM column from our dataset and just use petal length underscore class column for our machine learning algorithm model to prevent overfitting of data. Now, this was an introduction to how we can prepare a dataset using feature engineering techniques such as binning and encoding. I would now urge you to perform these techniques as well as other feature engineering techniques on a dataset that is relevant to your business practice. In this video, we will understand the basics of text feature engineering. In machine learning, it is challenging to deal with unstructured text data as there is inherent unpredictability of the syntax, the formatting, as well as the contents of the text documents. Additionally, there is a challenge to transform text into numeric representations that can be understood by machine learning algorithms. The first stage of dealing with text data involves pre-processing and normalizing the text, which is done by removing all HTML tags in the data that typically don't add any value in analysis of text. All uppercase and accented characters are also converted to lowercase and standardized ASCII characters. In a subsequent stage, all special characters that are usually non-alphanumeric are also removed as they do not add much value in analyzing the text data. Stop words, including articles and pronouns that have no significance in constructing meaningful features, are also eliminated to clean up the text dataset. And lastly, stemming and lemmatization are also performed, where the process of obtaining the base form of a word by removing the suffixes is called as stemming, and the process of removing affixes from words to get a base form is called lemmatization. Finally, wrong spellings are corrected to complete the pre-processing of the text data. In this video, we will learn about the concept of term frequency, inverse document frequency, and how it is used in text mining. In large text documents, common simple words occur very often, and performing simple counts of such common words is not meaningful in text mining. The TF-IDF model is a technique that is used to analyze text by using a scaling factor in its computation. This technique or measure helps us evaluate how relevant a word is to a document in a collection of documents. The metric increases proportionally to the number of times a word appears in a document, but at the same time it is offset by number of documents that contains that specific word. Therefore, commonly used words would rank low even though they appear many times in a document, as they are not relevant for text mining. The TF-IDF technique is a combination of two metrics, namely the term frequency and the inverse document frequency. The term frequency represents the raw instance count of specific word that appears in a document. The inverse document frequency represents how common or rare a word is in a set of documents. This metric is calculated by counting the total number of documents in a set and dividing that by the number of documents that contain specific word. Very common words that appear often in many documents will have an inverse document frequency that is closer to 0, and rare words will have a number that is closer to 1. The TF-IDF score essentially helps us vectorize a document and assess the relevance of each word in a document. This technique has application in machine learning for retrieving the information that is most relevant and for extracting the most relevant keywords in a document. In this video, we will get introduced to the bag of words model for text mining. The simplest feature engineering technique that is applied to text is bag of words. It is essentially a simple scheme of vectorizing features from unstructured text, that is, converting text documents into numeric vectors. In this technique, a text document is converted into a vector of counts, where each vector contains an entry for every possible word, and the dimension of each vector is a numerical number, say n, where n indicates all distinct words across a set of documents. The bag of words model holds the raw count of each word in the document. For example, if a word appears 4 times in a document, the feature vector will have a value of 4 in the position that corresponds to that specific word, thereby indicating the frequency of that word in the document. An important thing to note about this technique is that it converts the text document into a flat vector, which means that the original text structure has no value in this technique. In other words, this technique does not take into account the sentence structure, the word position, and the semantics. It is a simple and a heuristic technique, but has its limitation in understanding the semantic messaging of text. In this video, we will learn about another of text feature engineering technique called bag of n-grams. As an extension of the bag of words model, instead of using single words, we can account phrases or a collection of words that occur sequentially. This is known as the bag of n-grams technique, where n-gram is a sequence of n tokens. So the bag of words model, which uses single words, is essentially a 1-gram or unigram. The bag of n-gram model creates token by collating individual tokens into sequences as n-grams, where n indicates the word counts in each sequence. Bigrams indicate n-grams of the order of 2, and similarly trigrams indicate n-grams of the order of 3 words. Bag of n-gram techniques retain the original sequence of the text and therefore is more accurate at preserving the structure and semantics of the text. Bag of n-gram technique retains the original sequence of the text and therefore is more accurate at preserving the structure and semantics of the text. Now let us understand the bag of n-gram technique by using an example. For example, the following sentence, James likes small cars, will generate the following bigrams. James like small, and small cars. Whereas the same sentence will create the following trigrams. James likes small and likes small cars. The bag of n-gram technique is really useful in various machine learning applications, such as improving predictions of an autocomplete system and to train voice-based personal assistant bots. As an example, with the trigram training, model bots are able to understand the difference between sentences such as set the date and what's the date. Hi, in this video we will review a code that prepares the data for a TF-IDF problem. We will review an example for pre-processing of data in text mining. We would be using a Python Jupyter notebook that is set up on AWS EMR using Apache Spark. AWS EMR is a big data platform in cloud that allows us to access big data environments and processing tools, enabling us to run and scale big data jobs quickly. So first, let us log into EMR console from the AWS Management Console. To access EMR, let's type EMR in the search bar located on top of the screen. The search results that reads EMR should be the right one, which in my case is the top result. Let's click on it to access the EMR console. Once on EMR console, let's head to the notebook section located on the left navigation pane to view existing Jupyter notebooks on our AWS EMR. On the center of the notebook screen, we will find all the notebooks that will be accessible to our user account. On our screen, we find that we have one notebook named TF-IDF already set up. This can be viewed at the center table on the center screen. To open this notebook, let's first select the notebook by clicking on the radio button in the index column. This is next to the notebook's name in the center table. On selecting the radio button, we can select Open in Jupyter button located at the top banner on top of the table to access the notebook. We will now be taken to a Jupyter Notebook interface where we will be able to access the code. In the Jupyter Notebook interface, we will have one or more Jupyter Notebook files. In our case, the file that we are interested in is called as tf-idf.ipnyb. This is the first file on our screen, so let's head and click on the name of the file. Once the file is opened, we can see an existing code that prepares the data to run TF-IDF analysis. So let us review some techniques to prepare this data. Under the preprocessing header on our Jupyter Notebook, we have performed some steps to prepare the data for performing text mining analysis. The first step in the first cell under the preprocessing header is to view the sample data set to understand what we are working with. For that, we have used the syntax dataset, where dataset is simply the variable that houses or stores the sample data on which we would be running our preprocessing steps. On running the cell, we obtain some text displayed in the output cell number 2. The text displayed is in its raw form and cannot be processed with most ML algorithms, as it contains words in capital letters or words with punctuation that our algorithm may or may not understand, and other such issues exist with the data in the raw format. So let us resolve these issues one by one in the subsequent steps. On scrolling down to the next code cell, in the selected code cell, we are performing an operation to make all the words as lowercase letters. We are doing this exercise because otherwise our algorithm would consider the same word written in uppercase and lowercase to be two different words. For example, the word elephant written in uppercase letters and the same word elephant written in lowercase letters would be treated differently by the algorithm. To avoid such inconsistencies, we are making them consistent by saving all the data in lowercase letters. We've performed this function in code line number 2 of the selected cell. We have done this using the syntax np.char.lower with dataset in the brackets. Here, np refers to a numpy object and char.lower is a numpy operation that presents the data in lowercase. We have added this data in the variable lower underscore data set, which is also printed in line 4 to print the data. On running the cell, we would see that the output of cell 3 would have all the words written in lowercase letters. If we just look at the first line, the hare and the elephant, which was written in uppercase letters earlier, is now written in lowercase letters. Now let us scroll down to the next cell where we will remove punctuation from our dataset. Having punctuation symbols in the dataset caused the same problem as caused by having upper letters and lowercase letters in the dataset. So in the selected cell, we have a code that will remove the punctuation from our dataset. In line number 2, we have simply created a new variable clean underscore dataset and made it equal to the lowercase underscore dataset variable, which is the result of the previous cell. Then in line number 4, we have listed a set of punctuation symbols with the syntax punctuation underscore symbols is equal to the list of symbols that we want to remove from our dataset. Then in line number 6, we are iterating a for loop on punctuation symbols variable where each punctuation symbol is looked for in the dataset and removed and replaced with a blank space. Then in line number 10, we are simply displaying the clean dataset. Now let us run the selected cell. On scrolling down the result in the output cell 4, we see that the punctuation marks or punctuation symbols have been removed. Next, we can scroll down to the last cell where we will remove the stop words from our dataset. Stop words are the most commonly occurring words which don't give any additional value to our dataset. In our case, we are using the NLTK library to download the most commonly used stop words and then remove those words from our dataset. Based on the described algorithm, we are using a user-defined function called remove stop words. We have used this function in line number 2 of the selected cell. And as a parameter, we have given clean underscore dataset, which was the resultant dataset of our previous output. As a result of running the selected cell, we retrieve that the text with commonly used words such as the, I, am are removed from our text. One of the other commonly used technique of data cleaning is stemming. Stemming exercise is done to convert the words to its stem. For example, the word joking in our dataset would be converted to the word joke, which is its stem form. You can follow similar steps as you have performed in the exercise so far to stem your data. Based on your dataset, you may find other relevant techniques to pre-process your data, so keep on the lookout for those as well. In this course, we learned about different feature engineering techniques such as one-hot encoding, binning, transformations, scaling, and shuffling. Then we saw a practical tutorial explaining how to use encoding and binning on your dataset. From there on, we learned about different text feature engineering techniques such as TF-IDF, bag of words, and bag of n-grams. After that, in a practical tutorial, we learned how we could prepare the data for applying TF-IDF technique on your text dataset. In the next course, you will learn about problem framing and algorithm selection.